Hey there, Selman here, Physics 150 Lectures on YouTube. And we have another problem for you guys from Chapter 13 on Faraday's Law. So what we have here, and I'm just going to spell it out a little bit. It's not worth drawing a picture for this one. But what we have is that we are given the magnetic flux through each turn of a 210 turn automobile alternator. So we are going to say that phi, the flux, we're going to drop the subscript for a second, is equal to 2.5 times 10 to the minus 4 Tesla meters squared. Yes, that is a typo. Times the function sine of omega. Oops, that is not right. This is cosine of omega t. Cosine of omega t, where little omega is the angular speed of the alternator. Now we are going to just write this in a little bit more of a compact form. So let's write this as phi is equal to phi 0. This is just the magnitude of that trig function. And then, or not the trig function itself, but it's the magnitude of the flux times cosine of omega t. So now the phi 0 is the 2.5 times 10 to the minus 4 Tesla times meters squared. And so we are dealing with a automobile alternator that has 210 turns. So the total amount of flux through the entire alternator that we will call this phi capital T for total, is going to be the number of turns times the flux for each. So this is going to be n times phi 0 times cosine of omega t. At the same time, we have an additional piece of information here, which says that the alternator is geared to rotate 6 times for each engine revolution. So if we let capital omega be the engine angular frequency, then what that is telling us is that the alternator angular frequency is equal to 6 times that value. So that's another additional piece of information. So what is it that we want to do with this problem? It says for part A, if the engine is rotating at 1,000 RPMs or revolutions per minute, then find and what we want to do is we just want to find the absolute value of the EMF as a function of time. So what we have here is a time varying flux due to Faraday's law. What that's going to mean is that there is going to be a induced current that's generated by that, or rather an EMF and then an induced current. So we want to find the absolute value of that EMF as a function of time. So the way to do that is to use Faraday's law, which says that and we're going to use absolute values. The absolute value of the EMF is going to be given by the absolute value of dt of the total flux. Okay, fair enough. So now our job is to compute this thing. So let's just compute the time derivative of the total flux. This is t, capital T. So this is the time derivative of, well, what is it? The time derivative of? Well, the total flux was n times some magnitude of the flux times cosine of omega t. We don't know what omega is. We're still going to solve for that, but we're going to delay that for later. So how do I compute that time derivative? Well, what I do is I first recognize that these are constants. These are just parameters that are given in part of the problem. There's no time aspect to those at all. They can be pulled out of the derivative. So this is n times phi 0. Remember, phi 0 is just a constant. And so now what you have is d dt of cosine of omega t. And the way to compute this derivative, d dt of cosine of omega t, is to use the chain rule. What that means is you take the derivative of the inside, that gives you omega, times the derivative of the outside. By outside we mean the function cosine of omega t. So then that is minus sine of omega t. You can look that up in your favorite reference table. So what that means is that d total flux dt is equal to minus comes from that derivative, n phi 0 omega times now sine of omega t. But we want the absolute value of this thing, so we have that the EMF, absolute value of the EMF as a function of time, is positive n phi omega sine of omega t. Now we're almost there. We just need to figure out, so this is the function we're going to end up using. We just have to evaluate a couple of things. First things first, we need to find out what omega is. So omega, we were told, was 6 times the capital omega, which in this case means it is, so I'm 6,000 revolutions per minute. So let's do this one more time, giving ourselves a little bit more room. Omega is equal to 6,000 revolutions per minute. We want to convert that into SI units, so we're going to multiply by, well, we want to get rid of the revolutions, so there's 2 pi radians per every revolution. And then for every 1 minute, there is 60 seconds. And what you get from that is that omega is equal to 628 radians per second. So now we're almost there. We can compute the absolute value of this as a function of time is going to be, again, n phi 0 omega sine of omega t. Plugging in what all of these things are, you have the 210 turns, you have the 2.5 times 10 to the minus 4 Tesla meters squared. You have got times the omega value that we gave, so this is 628 radians per second, and then you're still multiplying by sine of 628 radians per second times t. So that's pretty cluttered. When you multiply all those factors through, what you get is that this is E as a function of time equals 32.99 volts times sine of 628 times t. Of course, there's some units in there, 628 radians per second, but you get the drift. So that is the final answer in putting in all of the numerical values where we could. Now part B, so this is the answer to part A. Part B says, determine the maximum EMF. So we want to determine the maximum of this. Well, if you look at this functional form, I'm just going to write it down a little bit more compactly. Essentially, what you have is that this as a function of time is equal to n phi 0 omega times sine omega t. Well, how does this function change? Well, n, phi, and omega, these are all constants. Omega is also a constant that's given as part of this problem. So the way that this function changes is when t changes. So when sine of this when this function sine of omega t changes, that's how it goes from maximum to minimum, so on and so forth. So what is the function of sine? I mean, maybe I'm making this more difficult than it needs to be, but if you just look at this thing, then its function, so this is sine of x and x, this is something along those lines. It reaches a maximum of, so it reaches a maximum of 1 and a negative of 1, or minus 1. So clearly, the EMF reaches a maximum when sine of omega t reaches a maximum, and that reaches a maximum of 1. So the maximum value that you can have for this is just when sine is equal to 1, which just means that what you're left is with n times phi 0 times omega. Or that's just the coefficient of the number that we wrote down all the way up here. By coefficient, I just mean this 32.99 volts number. So the maximum is just that. So we have that E max is equal to 32.99 volts. Of course, one last thing to add to this is that the sine function reaches, so I just want to, so that's the end of the problem, but one thing you might want to also consider is when it reaches that maximum. And so sine of x, or rather, actually it's better to just use the omega t at this point. So sine of omega t reaches a max of 1, right? So when does that happen? Well, we know that sine of pi over 2, so on your unit circle, sine reaches a maximum when its argument is pi over 2. That's equal to 1. That's just 90 degrees, right? So what we have is that sine of omega t, well, this reaches 1 when, well, you guessed it, when omega t is equal to pi over 2. It's also going to happen whenever the angle goes through another 2 pi. So you're gonna see this thing recurring. So if you add 2 pi to that, that's going to be, well, 2 pi plus pi over 2, that's going to be 5 pi over 2. You add another 2 pi to that, so on and so forth. Looks like 9 pi over 2, etc. So whenever it looks like, so for example, t, it's going to reach a maximum when t is equal to pi over 2 omega, or 5 pi over 2 omega, or for example 9 pi over 2 omega. So this is when these maximums occur. Okay, just thought that I should add that. Have a good day.